Oh yeah, yeah. So one comment on the like Hadoop thing. Um, I actually have not been doing Hadoop for 10 years. I just went to a conference recently that was celebrating Hadoop for 10 years. Actually, what's kind of funny is I always hated data, right? Like I was a services, or not service, well, yes, I like the web services, kind of that, like those challenges, distributed systems, but yes, anything data always had, Oracle tied to it, and it just wasn't fun. But now with right, like the advanced analytics and things, yeah, like the term analytics, I hated that, right? Because like that was even worse, like type of data. It was historical. It was weeks old, months old, whatever. But now with things like Kafka and streaming data and right, like the advanced analytics, machine learning, things like that. Yes, I got a bunch of questions at break about TensorFlow and people trying to use TensorFlow in different use cases. And to be very, yeah, like to be very frank, I'm not really seeing a lot of people, even in the Bay, that quite know what to do with like TensorFlow, right? Like Google knows what to do with it because they built it. They have their specific use cases, spam and right. Like, do you guys right like get those like auto reply things that show up on your like Android phone? Like, does anyone use those? Do you guys use them? I think they said probably 30% people use them or something. Is that consistent? Yeah, one of my friends sent me the auto reply to an email I sent her, and it was ridiculous. So, um, but yeah, I'm seeing like there's a lot of right like beyond the initial fun, right, like image classification and trying to figure out a dog and a cat and like that kind of stuff. People are starting to have a hard time. So we've been exploring ways to reuse those models, right? Like the term is called transfer learning or like retraining your model. So that's the concept where you take, right, like Google's model, the inception model, which has all the images and um, has all the weights and everything for this really, really deep neural network and kind of crazy neural network. But then take your right, like images or your use cases. One company that's actually doing quite a lot is this company Clarifai, CLARIFAI.com. And yes, right, like not surprisingly, one of their first beachhead, right, like business, right, like uses for this was porn, and more on the right, like user generated content trying to detect porn so that you can automatically take it down, right? Because otherwise you have to have a human in the loop. So there's ways to analyze skin and lack of clothing and things like that. So, but that was a case because the right, like Google data set itself was not trained on porn. But it's been trained on detecting right, like edges and faces and you know right, like different sections of the body and that kind of thing. Yeah, this is I'm just gonna stop. But um, so they still wanted to reuse that, right? And the right, like those neurons have right, like learned those kind of things. So it's been pretty effective. And then yeah, just recently I think Google slash YouTube right, like released a video, a right, like labeled video right, like data set um, for their right, like YouTube videos. And yeah, they've either right, like labeled some of them or right, like machine labeled some of them as well. So they've kind of thrown it out there to the community to see if anyone can come up with a good model that takes this data set and then can predict new videos coming in, which is kind of interesting because video is it's right, like image classification per frame and then it's time series, the sequence of frames, right? So it kind of mixes both right, like convolutional neural networks and then the recurrent neural networks for the time series. Okay, I've got about 30 slides, but I want to show, it sounds like you guys are kind of on the brink of using Spark and some of the advanced things. So I think, how much time do I have? As much as the bar, okay, got it. Yeah, what time is last call? That's all I need to know. Right, like, do you guys have Fireball here? Yeah, have you guys heard of Fireball? Oh, I think it was banned in Finland. Yeah, this is like the alcohol that like Americans drink like crazy. that turns out it was banned in Finland because they realized it contains what's the stuff, really, antifreeze, right? Which explains why I have such a horrible hangover every time. It's like super sugary and right, like girls love it, it's great. Yeah, like from that standpoint. But it's like $12 a shot now, and like yeah, the whole bottle at the liquor store costs $12. It's pretty cheap. So right, like what's the shot around here? Yeah, what do you guys drink? Just vodka. What's that? It's a surprise. Really? When? Really? Did Steve come here? All right. Very special. Okay, let me mention a little bit about me. This is oh, is it real? Oh, sorry. Okay. Yeah, part of the pancake stack, right, like the inspiration for the pancake stack came from this 3D pancake laser, or yeah, not laser, but right, like pancake batter printer that I stumbled upon. It was a Kickstarter thing, and I was looking for a fun name for the next evolution of the SMAC stack. Yeah, so I think Oleg mentioned SMAC stack is Spark, Mesos, Akka, Cassandra, and then Kafka, right? Like someone asked about Mesos. I think it was you, right? Yeah, that was asking about Mesos and if it's required. It's definitely not. People when right, like they hear something like the SMAC stack, it's just a convenient, kind of fun thing to say. But right, like me personally, I see more of the Spark standalone, which was the thing down here that is part of Spark, especially for right, like newer systems where you don't have this like legacy right, like MapReduce that's bound to Yarn and all that. If it's a total greenfield project with Spark, you can just go with the Spark standalone. It actually scales pretty well. And yeah, I mean, I've seen very, very large clusters. Right? In fact, Databricks, that was my old employer, their whole product is a slightly modified version of Spark standalone. And they support, yeah, hundreds of customers. Yeah, so Pancake Bot, it takes about 45 minutes to print a pancake. So it's not really that efficient, but it's pretty cool. It comes in red too, if you're interested. Yeah, so I started this company, Pipeline.io, I think back in June. Apache Spark contributor, Netflix open source. Yeah, has anyone used the Netflix open source projects? Like, yeah, which projects have you used? Yeah. How about the Rally Hystrix, the circuit breaker? Yeah, I have a demo of that. Okay. Fane is that the Mesos project?
No, it's wrapping around
Ribbon, yeah. Eureka, yeah, got it. Yeah, I'm still using, yes, I just switched to use Kubernetes. I'll show like a slick demo on that. And I've been able to rip out the Eureka stuff. Yeah, I was still using Eureka, right, like mainly for the Hystrix to get the distributed Hystrix and Turbine and all that. But there's the guys from right, like Red Hat have created or have been working on this project called Fabric 8. Yeah, it's like Fabric 8 and then .io. And yeah, they actually rewrote right, like the core ones, right, like Chaos Monkey, and to not depend on Eureka and instead use the Kubernetes DNS. So because I'm all Kubernetes, that fits in nicely. I've got this meetup, yeah, the Advanced Spark and TensorFlow meetup in San Francisco. I think I have a slide on here. Yeah, we're up to 4,600 members. I just checked today, top 4 Spark meetup in the world, which is kind of cool. It's funny, it's like 3 San Francisco, and then right, like the ones below it are all, it's like Bangalore and right, like Hyderabad and all those. So actually, oh yeah, Talon. Yeah, I mean, Talon's on there somewhere. And I think I'm the number 1 TensorFlow meetup out of like 3 that are actually that have found the tag to put on their meetup, which is half the battle. yeah, Chester's my buddy number 3. I have to figure out a way to take him out in a nice way. Um, most of the like demos and things that we do for, yes, I have a workshop too. Yes, I have a slide on that in a sec, but all comes from this repo, flux capacitor / pipeline. It's a pretty burly like repo, but most of the demos I'm going to show today come out of that. I've got the second generation, like I said, is I've moved over to it's like Kubernetes, and then it's all separate Docker images now. So this one is just one big ass Docker image, 17 gig Docker image, which is it doesn't download that quickly. But yeah, I have about 6,000 polls on it. That slide I didn't update, but yeah, that one is up there. Some of the things we do, we're focused mainly on trying to empower. Yes, I'm like not a business guy at all, but the types of things, right? Yeah, so like when I joined Netflix, for example, it's this environment where the developers actually have a lot of power. We have keys to production. We have keys to all the data. I don't know if we're like legally supposed to, but yeah, right, like behind the firewall, right, like anything goes. And you can push, so right, like you don't have this like DevOps group or this ops group that you work with. You are the DevOps group. So right, like you really get to learn about right, like the underlying OS and like system performance, things like that, things that as a typical application developer like you probably wouldn't get access to. So I started seeing these same problems with like data science groups. Yeah, so people that go to work at Netflix, right, like love this freedom, and right, the sort of corollary there is that there's freedom with responsibility, and you have to right, like be very careful when you push out right, like new builds and things like that, right, like new releases that you can quickly roll back as well. So they do these things that are called Canary releases. So let's just take just a regular microservice. I was on the streaming team, right? So the team that would collect all the play events and everything. Whenever we'd push out a new build, we would push a Canary, right? Just one instance that was running along the other 5,000. And we had this tooling, right? Like so Netflix, there's huge tool, right? Like tools teams. And I mean, these are like, right, like really advanced developers that, because that's the whole core, right? Trying to speed things up, trying to push out releases faster. And so with that, you had this like Canary analysis where things that we were looking for, right, were like error counts, of course, things like that, but also system performance, right? Like JVM, the heap size, did this new build, is the heap blowing up? Right, like context switches, right, like all the typical things, the CPU load and all that. We when I was there, it was manual. Right when I was leaving, and in fact, this is one thing that they have not yet open sourced that they keep saying that they will, is the automated Canary analysis. Yeah, ACA. So that's the ability. Yeah, so internally, it's all automated now. You just push it out, and because it's not that big of a deal to push one bad server like amongst 5,000. So these are all stateless, so people just like periodically might periodically get a blip, but it will do that comparison for you and kind of hint and say, yeah, things are a little bit yellow or red, so it would pull it down. But I mean, giving like the ability to extend that to the data scientist as well. So picture from like an IPython notebook, right, like the ability to push out a new model, right? Like not the runtime or anything. I mean, yes, obviously the runtime's there, but for them to, right, like do this like rapid experimentation. So surprisingly, right, like there's a lot of tools that get you right, like pretty far through, right, like your, it's simply called machine learning pipelines, right? These pipelines, but yeah. So like most pipelines sort of end at the training phase, and then from there people hand it over to like a production engineering group, and then they take the model and rewrite it in Scala or Python or Java or something, and then stick it behind like some Flask service, and no one really like knows what happens. So the point that we're trying to get to, and we're like pretty close right now, is where you can either push the model out live to the live running servers, or to one Canary and then like check it and then push to the others, or you would commit the model in like PMML format, right? Like for example, that would trigger like a back-end pipeline, like a Jenkins pipeline, right? That'll package it up into like its own Docker image. It would label the image with the same GitHub, hash, right? Yeah, that was committed, so you can trace everything back, and then push out the Canary, right? Like using Kubernetes, and like Kubernetes labels, right? Like with Kubernetes, you have a load balancer, and then you have your like auto scale groups and servers that you like label, and then that's how they go in behind the load balancer. And then once you pull the label off, it'll pull it out. And then let's see, yeah, so model deploying and testing, scaling, and then this concept of like online model training. So we're going to do a demo here in a sec, but as data comes in from the like end user, yes, I mentioned before about there's kind of a main Kafka like topic or queue, and then from there, like the application teams can kind of split it off and like pipe in. So the red, if you continue with the red down, that's kind of the cold path, right? The boring path. But the cool, fun path is the purple path. And so that's where we're actually training in real time. So each night, like for example, Netflix would train on all of the data. So this could either like be done manually. Typically, it's not done manually. Typically, it's some cron job or something like that, right? Some scheduler, and then they seed that data. So that might take 6 hours or 8 hours for like 100 million users, huge clusters. You would seed that model for the real-time path, starting at let's say 6 a.m. or something, right? And then throughout the day, it's taking in batches of data, play events and things like that, to figure out what people are actually clicking on, and like making small tweaks to the model, right? And then like sort of pushing it out, right? Like maybe every hour, maybe every half hour. And so those are the actual. It's sort of a near real time. And if there's not much near real time data, it'll just fall back to the batch data, from like the night before. But yeah, so that's that third bullet point. And then model optimization. Yes, obviously this is like a heavily studied topic, but the way that like we're thinking about this is, picture if you have a decision tree, for example, that you've trained, and it's in PMML format or something. It's just a big blob, and then like the ability to actually take that model and then generate Java code or generate like C++ code. Yeah, this is like pretty heavily studied stuff, but like the ability to sort of squash down trees. Some of the customers I've been starting to work with recently, like guys like Cisco. There's like so many teams within Cisco. They're all doing the same thing. They just don't know it because it's like a 500 billion person company or whatever. So I get the same calls and the same emails. I'm like, yeah, do you know this group? They're like, no, just talk to us. Don't worry about that. It's all fraud detection, basically, is what everyone's doing, right? So the ability to squash down, and these trees are 20,000 levels deep and like crazy stuff like that. But there's certain branches of it that can be squashed down, and so that would help performance-wise, right? Like versus doing like pushing out PMML, which has to sort of be interpreted, right? So the ability to actually generate like native bytecode. So there's this project. It's called Project like Janino, Janino, that's used by Spark actually, which is where I got the idea to start taking a look at it. That can actually generate like bytecode on the fly. So so something like that, and like the ability to actually send the code over to the cluster and then have like the cluster compile it and then deploy the new model is really pretty powerful. So our deliverables, we don't make money. We're classic San Francisco company. We're just a cost center. So everything's open source. No one really knows how to make money on this stuff, and I agree to be one of them. So the Flux Capacitor, and then of course the Docker, all the Docker. So right now, if you go to the Flux Capacitor parent like organization, there's going to be probably 50, or there's about 25 different projects, and yes, each one has its own right, like separate Docker image. So yeah, I think for this talk we'll talk about neural networks, GPUs, TensorFlow, TensorFrames. But real quick, oh wait, yeah, I'm looking at my slide, which is the next one. Yeah, this is the workshop. I was just in London the other day. That was the smoking night. Yes, I didn't realize how many people smoke in Europe. There's a lot of smokers out here. Yeah, I was in Greece and I was just like, it's not legal to smoke inside bars and restaurants in Greece, but everyone does it. It's just like, yeah, it's funny. Yes, I was surprised by the talent in Greece, by the way. I know nothing about that city except for, like mathematics and all the things that have come out of there. But yeah, I keep screwing with this. There were probably, I think 130 people showed up to the meetup, and they were asking like crazy questions, and they're really using TensorFlow already and stuff. I was like, man, yeah, you guys are busy here. And then, yeah, I found out that yes, I shouldn't talk about people's salaries, but this is so completely ridiculous. So the people I was talking to, which are data scientists and like it was like 10,000 euro, like per year. Is that? Yeah, I don't know how much you guys make or anything, but that's really low. Right, but of course they pay like 150 for rent and all that, So, yeah. So yeah, workshop. The next one's in Brussels, tacking it on to the end of the Spark Summit. Yeah, is anyone going to the Spark Summit down in Brussels? Anyone? Really? It's a really good conference, not just for Spark, but even for streaming and for sort of academic type things. These guys are from Berkeley, and they're very really conscientious about what they who they pick to speak up on stage. Yeah, they never pick me, of course. Yeah, so I think we'll cover this, but actually, can we do like a quick demo? If you guys can pull out your phones. Oh, this is where I can't. Or your laptop, but yeah, I assume it's easier to get your phone out. This is the famous Spark After Dark demo. This is the creepy dating site I started to build. I was just tired of like movie recommendations, and I wanted to class it down a little bit. All right, so Spark After Dark. Here's your guy's unique ID. Yeah, everyone gets a unique ID. Actually, it's probably not unique. It's JavaScript generating it locally, so there's no central point. So could very well not be unique. And if you can click, these are American actresses and actors for the most part. So again, yeah, I assume we're like open-minded people. Yeah, we're okay selecting same sex for purposes of, I don't know, just going for coffee with these people, right? You don't have to date them or anything. Or like, not that they would talk to any of us. Yeah. Oh, the URL. Yeah, I was wondering why no one was actually clicking on anything. Okay. Demo.pipeline. Hang on, I can make that bigger. I'll make it bigger. There you go. I can't figure out how to make the URL in the browser bigger. Demo.pipeline.io. And select some people. Okay, and I'm going to run, this is the slow path. This is the non-cool path. Meaning, so we're being the people in that like upper left of that architecture diagram that I kept showing. And we're submitting ratings to Kafka through the like Kafka REST API. And those end up in Spark Streaming is pulling off Kafka, and those end up written to Cassandra. And now we're being data scientist person, that was down at the bottom. check one thing. Ah, crap. Yeah, I don't have one. I forgot to start one of the jobs. So you're going to have to click again, but the screen isn't mirrored here. It's kind of weird. I have the fast path running, but not the slow, boring path. All right. This is the Spark admin UI. Right, like, does anyone use Zeppelin? Do you? You do Scala or do you do Python? Scala, yeah. Are you on the latest Zeppelin? Yeah, how about IPython? Did anyone use IPython? Yes, everyone, basically, yeah. All right, so I think, yeah, okay. So if you guys don't mind, just hit refresh and you'll get a new ID, don't worry. Okay. You can click the same people. Anyone know who this is? My favorite person in the world. Sofia Vergara or whatever. I love her. I purposely don't have the yes, I'm not checking for like double clicks, so you can click as much as you want. It'll, yeah. So I always stuff the ballot with her just to make sure she ends up there on the top. Well, Johnny Depp. Yeah, anyone know this guy? Franco. Yeah, he's a super smart guy, by the way. My old neighbor, like, knows him pretty well, and he's like, he's not just some goofy dumb actor person. Okay, so you guys were clicking around there, I assume, right? Got your vote, cast your votes. So let's do live recs. Oh yeah, the first day when you start Netflix, they like make you send an email to the entire company saying what your favorite movie is, what your favorite TV show is. Yeah, what's your favorite TV show? Or yeah, your favorite movie. No idea. It's probably not on Netflix if really no matter what it is. Yeah, so I like pretty much 80% of the time people would say Shawshank Redemption. There's something about like being associated, like saying that is your favorite movie that people, even people that like haven't seen it, like say. It was funny. Like it would be 3, 2, 1, boom, Shawshank Redemption, right? All right. So this notebook is just doing a top K basically, which is a form of a model, but just like aggregating. Let's see. I think my resolution's a little. Ashley Judd. Okay, right on. So this should show up. It should be the same people here. Come on. Did this run? All right. I'm not gonna spend too much time here. About the recommendations. Recommendations. Yeah, so that actually came from, let's see, that's the second. Yeah, so this is kind of, like the like old school way. So you wouldn't typically like be doing this manually, but what's cool within Zeppelin is that you can actually pick a notebook and then run it like a cron job. There's like a little cron thing and it has cron syntax and all that. I don't know what's going on here. Oh no. Okay, now let's do the cool one here. This is the one I spend time testing and not the other one. The cool one here is you're actually, yeah, so as you're like clicking, it's actually continuing. So this is that fast path, right? The URL for the cool one is the same thing / realtime.html. And it should be showing. Why isn't it showing? It's showing item to item similars, but not these. Alrighty. Yeah, here's your Hystrix dashboard here. Yeah. So as ratings are coming in, things like that, probably a little bit too soon to jump into. But yeah, so this would actually, if I pull up the architecture diagram real quick here. Architecture overview. The slow path is the one in red. So right, like this is us selecting. That's right, like adding ratings. Spark streaming is down here. The slow path is just storing in here. Then we have to generate them through Zeppelin or through some sort of cron. And then the fast path is the purple path, where it's actually it's making small little tweaks to. Let me find the model here. Why is this notebook not coming up? Yeah. Yeah, sometimes if there's like other people hitting it, like it gets all confused, crazy. Anyway, yeah, so we're effectively like doing matrix factorization, where we're taking a snapshot of the like users are the rows, and then the 30, there's 15 actresses, 15 actors are the columns. We're like taking a snapshot of that each night, and then factorizing it into two smaller matrices, right? That when like multiplied together get as close to the snapshot. So that lets you fill in some of the sparsity with the ratings, and then you can start to make recommendations. So the fast path takes that snapshot or those two smaller matrices, stores them, and then as new data comes in, it's making small little tweaks. And then it's recalculating every hour, or yeah, here it's every few seconds because it's not that much data. And then we're like regenerating recommendations. So that's what we see. Part of it is coming back here. This is like item to item similarity. So once we can, I'm like missing the key image here because this notebook's not coming up. Yeah, so once we can represent, right, like items now, each item can now be represented by one vector, right? Like we can actually put those items into vector space and then find similar, right, like items around that way. Yeah, in this new smaller vector space. All right, so that's one kind of fun demo there. Yeah, we actually build that. That's what we build in the workshop in a much more successful way. So that's, yeah, both batch and the real-time recommendations. I want to show, we mentioned some of the Netflix stuff since I'm here. This is right, like an example of circuit breakers. So here we have 3 circuit breakers. Now, right, like, do you guys know this concept of a circuit breaker? This guy, I think it's Michael Nygaard, has a book. That's a weird title for a book, but it's like one of the best architectural pattern books that I've seen in like quite a long time. But this concept of like a circuit breaker is, so at Netflix, yes, I was on the streaming team, which was an edge service, they called it. So right, like devices talk to us, right, like directly, and then we talk to many other Netflix services that were like behind the firewall. And so yeah, like this would be an example of, this is the user item prediction service. It's using the command pattern. That's why the term command is in there. And this could depend on many, or yeah, right. Like let me just kind of describe how at like Netflix we did it. So our streaming service, all the devices came through us, and then we talked to the prediction service. If that prediction service, right, like ever went down, we wanted to have some fallbacks that were put in place. But there's two types of being down, right? There's it being down, like it's just not available, which is a fast fail, which is actually good. Or there's the latent down, where maybe it's like some sort of, right, like an internal denial of service attack, which isn't really usually, it's not like intentional, but it's definitely possible if one service scales up and forgets to tell the downstream service. So yeah, so in, yeah, so for this kind of situation where the dependent service was down, we would flip this circuit open and start to return fallbacks. So for the prediction, for like recommendations, for example, we would just return like a global top 10 movies. So it would be like Shawshank Redemption, that would definitely be in there. It would just be JSON that is burned into the EC2 instance, because that's all in a state of failure that you can really rely on. You can't assume any like network or any database being available. So yeah, we would physically burn in with each image this like JSON fallback. So yeah, let me simulate. Actually, gonna simulate a. Oh yeah, release it. Yeah. Yeah. It's this project from Netflix. It's called Hystrix. Is the circuit breaker thing. So I'm just gonna simulate. I'm using JMeter here, my old friend. It took me like 4 years to actually understand this UI, so I'm trying to amateurize the steep learning curve by continuing to use it well past its prime. So let me start up a bunch of threads, in 2000 to be exact. And it's going to start pounding. So here we're seeing a bunch of, yeah, so this purple, this is the rejected one. So this is this is the thread pool here. So pool size. And at some point, right, like we would have to tune, right, like the actual thread pool based on expected load and that kind of stuff. But yeah, this can tell you how close you're getting. Yeah, green is obviously good. Purple is not good because things are being rejected. It's still kicking into the fallbacks. It's just not. It's in sort of this degraded state, right? So yeah, so these three services actually, for this example, are the edge services, and they depend on Redis. So if I went and killed Redis, we'd start seeing some of these circuits open. In fact, yeah, let me try to do that. It's probably going to burn me elsewhere, but oops. Where did my kill Redis? There we go. Yeah, so these circuits are now open and it's returning the fallbacks, which actually is fine because now this gives the Redis group or whatever time to scale up their cluster. It sheds the load. From the user's perspective, they're still seeing recommendations. It's just not personalized, right? So yeah, we would rely on these very heavily. Yeah, in fact, this changed our whole concept of like uptime and that kind of stuff, right? So if there was ever one service that would get overloaded for any reason, right, like all the other edge services would just crap out, and then like you would start seeing customer service screens on your devices. So we kill JMeter because it's chewing up all my CPU there. Oh yeah, and now my pager duty's going off because I killed Redis. All right, go pager duty. Okay. So that's that. Let me do one thing here to get set up for the next demo later. I'm trying to make this more interesting than just a bunch of slides, but I think I'm going to switch back to the slides in a sec. Let me do start. Okay. All right. Yeah, so later, once that, those services start up and settle down, I'll show you guys actually are like building a model and then pushing it out to the live running server. It's kind of cool because we'll build a model with Spark, convert it to PMML, push the PMML out, and then we'll generate a model and then generate Java code and push that out. TensorFlow, I've seen a few different people try to do matrix factorization and or like alternating least squares and other collaborative filtering techniques with TensorFlow, and it never ends up. There's a couple out there, but yes, anytime anyone ever puts one out, someone comes in and just tears it apart and says it doesn't work because of this reason. So yeah.
I guess the biggest limitation is the amount of memory that you do.
What's that? I have 30 minutes. Okay. All right. Let me go back to here. All right. So let's talk about neural networks. Who here has used these or studied these in the last 10 years? Because I was talking to one of my buddies who has his degree in AI from 1995 or something, and he's like, this is totally different than what I studied, right? Just like a lot of the algorithms are, the fundamental concepts are there, but things have changed a little bit in the last 20 years. So yes, right, like just like any other type of supervised learning, you're trying to minimize loss, right? You've got labeled data, you're trying to build a model off that labeled data, hold out data that has not yet been seen, but that you have the answer to, right? Like that's also labeled data, and then validate your model by passing in that held out set. The way that these neural networks work is, right, like they actually start off with like random guesses. And so depending sometimes on the types of random data that you seeded it with, or that right, like you initialized the network with, could take a little bit longer to actually get, you could end up in like local minima and things like that. So, but the whole concept is you're trying to get to this as low error as possible. You figure out what direction, right, like you should be going in and how much. And you then back propagate. So you have this whole amount that you need to back propagate to all the individual nodes within the network, right? So you have the answer key on the end. That's what you're training with. You've started with these, right, like random weights, and it's basically multiplies and then adds at, right, like each of the nodes. You're like multiplying, right, like between the edges, and then you're just adding at each node. So what you have to then do is figure out how much to tweak each of the neurons that led into that fed into that error. It's not going to be uniform across all of them, right? So partial derivatives come into play there. You can figure out with respect to a particular input how much you should change. Let's see, the old chain rule. Yeah, and then once you've actually trained, right, like your network, when you're doing the right, like prediction, right, like later on with new data, it's like the exact same network. It's a forward pass through, and there's no back propagation, right? So those weights get stored. And let's see, convolutions. This concept of convolutions, if you kind of think of, you're kind of scrolling across an image, you pick some sort of filter, right? If you're trying to look for this particular pattern, you would then scroll across, and so I guess the term is, right, like convolve down, and so you're basically sort of downsampling, right? So that goes on, and here, so like this is a case where you have two GPUs. So there's one single image. You're splitting up the choices. So you have like a fixed set of filters, right? Like different patterns that you're trying to look for. You split those filters up so that each filter, each GPU is responsible for like one set of those filters, and both GPUs go and like go over that whole image and then pick up, and yeah, that's how, right, like and at certain sync points, right, like these share the weights that they've learned, and they just basically average between the two GPUs, and typically that's happening on the CPU. So like, yeah, so that's why like you don't want to do it too often because it's a bottleneck, but if you don't do it enough, then things start to stray, right? Let's see, one really cool like use case here. Have you guys heard of Stitch Fix? You might know Stitch Fix, some of the conferences. Yeah, these guys, they ship you 5 pieces of clothing. It was just women to begin with, and now it's men. Yeah, so they use, right, like machine learning at all different phases. They ship it out. There's a human that's in the loop, like a human stylist that works for Stitch Fix. They actually see the recommendations, right? And then they, from like the 100 recommendations or whatever for that particular user, for that customer, pick the top 5. It's kind of a tricky machine learning problem when, like the human gets in the loop, because that natural feedback that assumes that the user has not chosen certain items, right, kind of gets really confusing a little bit. But yeah, they actually use neural networks. They take their most popular items and then run them through and have these neurons pick up certain features, right? Like if it's short sleeve or if it's like a V-neck or like things like that. And then they take their shittier clothes and they run it through. And that makes little small changes to the less popular things. They send that back to the supplier of the less popular ones and say, hey, yeah, maybe you should add stripes this way, or add, go sleeveless, yeah, that kind of thing. And then when you send back, right, like your items, you have to explain why. So they do a bunch of NLP on that, right? Like they actually analyze your comments and then that can associate and start to learn some things about you based on that. Yeah, so they have collaborative filtering, but the user is the stylist. And then, yeah, they use neural networks for like this kind of stuff, and then they use like NLP for comments. All right, so this is a good use case for convolutional neural nets, which is going around picking up features on these. But like for anything fun and sort of real world beyond the typical image classification stuff, you're going to end up needing some sort of recurrent neural network, right? Because there's time series, right, that's involved here, and state actually matters, right, from like one layer to the next. So here's actually an example of character-based RNNs. So typically, when you think of like natural language processing or speech, text, so like text prediction or like text generation, things like that. If you're trying to generate captions, for example, you think of words, right, like being the token, and you're trying to find surrounding words, and the context of the word, right, like helps define that word. Here, there was a paper that came out of Microsoft, I think even just a couple months ago, where they found that a three character token, or right, like token, is the most optimal. But yeah, this is kind of the like basic case here, where we're treating each token to be just one letter, and then learning and then making predictions. So yeah, here's the classic like hello, right? Like the first L, because it's been preceded by an E, has higher probability that the next letter will be an L. But when it sees two L's next to each other, then it learns that O would be the next. So yeah, this is kind of interesting because it kind of separates you from having to do some of the feature engineering where you're like finding sentences and co-locating words and like doing all these weird things like like combining 2 words, like the phrase senior developer. If you're doing like some sort of resume app or something like that, you would want that token to be like one thing. So yeah, here you can actually learn at the character level. Yeah, so again, Microsoft actually came out and said 3 characters in a row is.
So I have a comment there. It's
Yeah.
a bit like sparse streaming. What matters is that the dependencies are in two directions. There is a direction from the input to the output, and there is a direction between given pairs.
Right. Yeah. It's the fact that so you're drawing the analogy with Spark streaming because state before can affect. Yeah. Got it. Okay. Let me keep going here. GPUs. Yeah, lots of ALUs, right? Control logic within GPUs. Yeah, these GPUs is very bad. These are meant for like single instruction, like multiple data. So this is that term vectorization, like Oleg was talking about earlier. You want to pack as much data in and run like the exact same instruction. That's optimal for these things.
So how much RAM do they have usually?
Yeah, 12, 16 gigs. Yeah, not that much. That's one big difference between GPUs and CPUs is the amount of RAM that they have access to.
The memory throughput is like 10 times faster, right?
Yeah.
The latency is high, but the throughput is very high.
Yeah, these are optimized for throughput for sure. Yeah, here's a case where if this is your code and there's a branch in here, this is where in like GPU land, if there's tons of threads going through, so here they're all doing the same thing, blue. And then when it comes to this, certain threads have to stay idle, right? And there's 4,000 of these cores. So there's threads running on each core. So yeah, the more branches that you have here, or if you have data dependencies, I think that's my next slide here. If you have, this is all, so this is data parallel, right? So so all these can happen in parallel. Whereas here we have a data dependency on A, and then C depends on B kind of thing. So that's not good from a GPU standpoint. Right, like has anyone done any CUDA programming or anything? Yeah, it's barbaric. Yeah, there were 2 people.
It's very easy to do it slow.
Wait, what's
that? It's very easy to do it slow.
It's and like the NVIDIA guys spend so much time building these profilers to tell you how shitty your code is. That like why don't they spend that time making it so that you don't it's not possible to write shitty code. Here's physically this was actually news to me. I took a GPU CUDA course this summer and didn't realize that actually there's this concept of a streaming multiprocessor. That's actually between versions, so off of the actual manufacturing line or whatever, these things all have these GPUs all have the same physical architecture. They sell them to you for your laptop, right? Like they'll actually disable 2 or 3 of them and just leave one going. So it's just classic manufacturing thinking there, where it's cheaper to just build the same one. But yeah, these streaming multiprocessors actually are the hardware that then schedules things onto the cores. Let's see anything else there. Yeah, there's an L1 cache here. Let's see, it's called the texture cache that comes from texture rendering and that kind of thing from graphics. Yeah, there's a shared memory. Yeah, of course, registers, constant memory. Yeah, here's a way. Yeah, like there's an so this is actually a live GPU. This is the Amazon. I think it's the G288XL or something. Has 4 GPUs. Each one has, I think, 12 gigs of RAM. So like the whole trick is trying to figure out when it makes sense to go to the GPU, because there's data transfer costs there, and there just isn't a lot of room to put things there. So like the new CUDA 8 has this concept of shared, or I think it's called unified memory, where you can basically address both CPU and GPU memory. It just kind of makes it sort of makes it less likely to write slow code, where it can kind of do little optimizations, like while threads are waiting, it can start to load data in from the CPU into the GPU, things like that. All right, TensorFlow. It's a general purpose numeric or like computation engine. This is something Google is pretty like adamant about saying. It just happens to also be good for neural networks, right? The one big differentiator I've seen, this concept of tensor board, right? So this is the ability where you can actually instrument your code so that during training, right, like you can keep an eye on, right, yeah, so things like loss and certain parameters that you're trying to like keep an eye on. So this is like, yeah, like this is the kind of thing that right, like used to cripple right these neural networks, is that you didn't have a whole lot of insight into what was going on. This doesn't solve that problem. It's still kind of a mystery as to why certain neurons pick up certain edges and things like that. But this gives you more right, like insight into the training process. So or like this, so this would let you, if you see your training start to plateau and it's not making any progress, you would just kill it, right? Like versus just letting it run and run and run. So yeah, kind of nice. And like you can actually do multiple models, right? Like you can train multiple models and they show up with like different colors and you can see which ones are training with like different learning rates and things like that. Yeah, it's right, like DAG based, which is similar to Spark when you're right, like building up the sort of operation plan, right? So for example, right, like classic neural network, it would be like a bunch of multiplies and a bunch of adds, and then yeah. So let's see, it's yeah stored in protobufs. Yes, obviously Google loves protobufs, and it's similar in concept where within TensorFlow, right, like within your Python code, you're actually building up sort of a logical plan that then has to get converted into physical operators that run in C++ and that kind of thing. And yeah, there's this library called tflearn that's essentially a scikit-learn or like drop-in replacement, but it's for TensorFlow. So that really gives you the ability to use distributed TensorFlow and also participate in really TensorFlow serving. So one cool thing about TensorFlow serving, like this actually highlights the sort of prediction layer, right? Yeah, that a lot of people, like I said earlier, just kind of push a Flask server out, or just like a sort of like an ad hoc Tomcat server or whatnot. So TensorFlow serving is a first-class citizen, right, like within TensorFlow, and you can actually deploy models alongside each other. It's constantly listening for new models. You can build your own right, like strategies for right, like blue-green deployments, that kind of thing. But right, like one thing that's super cool about TensorFlow serving that is given to you for free is it'll actually batch up right, like multiple requests coming from right, like different right, like end users or right, like clients. So think of, yes, I had my buddy draw this out because yeah, he's pretty good at explaining this stuff. But think of if we want to batch this right, like multiplication. So like the whole right, like concept here is to try to batch up operations to feed to the GPU. Right. Yeah. So otherwise, if you're just kind of taking one small right, like matrix multiply, yeah, this is a matrix times a vector. You're just going to be doing like a whole lot of communication for just right, like really, really small like operations. So here's a way where you can actually kind of batch these up. You would put this in like the upper left corner. You would go right, like yes, a corner to corner, and put this guy there, and then you would run right, like the entire calculation on the GPU, and then yeah, when it comes back, you can right, because you know sort of where these boundaries were, right, like then you can yeah, so figure out each right, like client's answer and then split it back up. Yeah, so you can really configure if it's like 10 milliseconds, 15 milliseconds. Yeah, the actual batch window. All right, I've got.
So one comment or question I wanted to ask. So in Spark, there is this DAG, right? And the jobs communicate only via this DAG and dependencies of partitions.
Yeah.
But I think in TensorFlow, there is a concept which is equivalent of a parameter server.
Yeah.
Where you can send asynchronous updates to the parameters of your model.
Right. So yeah, in Spark, yes, actually, I'm going to get to that with TensorFrames. I think what you're getting at is right, like there has to be some sort of central controller in these distributed systems for right, yeah, there's like certain calculations happening at the partition level, and they all have to come together and get merged somehow, right? Is that what you're getting at? Okay. Yeah, so right, like TensorFrames is where you have data frames within Spark. So there's data that's spread across the whole cluster. And you right, like essentially push out your TensorFlow code that's written in Python that can then operate on just that partition. But at some point, right, like that data has to come back and all get merged. And so yeah, there's two things here. So, right, like TensorFrames are basically this bridge between the Spark JVM and the right, like the underlying TensorFlow C++. It uses this project called Java CPP. Yeah, has anyone like used this? It's pretty slick. So, and yeah. So Java CPP has this sort of side project that has a bunch of this stuff implemented for specific projects like TensorFlow, like like Cafe and things like that. So the one downside is that you physically have to install the TensorFlow C++ runtime on each node. So it just kind of complicates some of your like Ansible scripts or whatnot. Yeah, this was developed by one of my old coworkers, Tim Hunter. His whole PhD is in tensors from Berkeley. So as I always call him Mr. Tensor. Yeah, I don't think he likes it much. Why TensorFrames? It's kind of like the best of both worlds, right? You've got, yes, I call it legacy Spark support. It really gives you like access to all of your Spark jobs, right? But now you can kind of slip in TensorFlow and yeah, let's see if this makes any difference, right? Yeah, so you can kind of mix and match. You get the distribution of Spark, which everyone like understands pretty well, and you have this kind of central controller, which is the Spark application itself, the Spark driver, that's like controlling all this. Yeah, that can do all the like merging when it comes back. Yeah, TensorFlow is DAG-based, similar to Spark, so just trying to reason through it. And then this concept of like data parallel model training. So like again, this is where we take one single model, we push it out to each partition, train, and then get those gradients back, merge the gradients, and then make the adjustments, right? So it kind of goes back to, yeah, so you can either do multiple GPUs on one machine, or you could do multiple like GPUs on like different machines. You can mix and match CPU with GPU. Let's see. Yeah, so essentially the Spark like master the driver becomes the parameter server in this kind of case.
So I guess in the Spark context, it will not be asynchronous, right? The merging of the parameters, like previous partitions with TensorFlow finish, and then you aggregate something.
Right.
Well, I think in TensorFlow in general, it's asynchronous. So.
Yeah.
Which may or may not be a problem.
Yeah. And there's like different strategies. Yeah, because I know Facebook, right, like they actually do like eventually consistent, right, like parameter server merging, because there's so many happening, and it's not that big of a deal if you don't get the exact
hog wild.
Exactly. Yeah. So there's actually not a lot of serialization going. It's not as much serialization as you would think between the JVM and C++. Let me see here. All right, I think I have one quick example. Show you guys some code here. So here we're just doing the import of TensorFlow. Here's the import of the custom TensorFrame library. This is sort of maintained by Databricks. It hasn't been touched in a couple months, so I'm actually kind of curious this week if like they're going to announce more first class. Yeah, right. Yeah. So their customers have been asking quite a bit about right, like TensorFlow and that kind of stuff. So yeah, that's why I think they're they're most likely going to have something coming out this week. Yeah, here, this is kind of where we're like mixing and matching. So this is just typical Python Spark code, creating a data frame, and now we bust into some of the TensorFlow stuff, building up this DAG. There's this concept of blocking or like tiling within TensorFrames, which can sort of operate on like different chunks of the data, right? Instead of doing it per row. All right, there's another one here. I upgraded to Spark 2.0 the other day, and it's like, yeah, a bunch of stuff is busted. But yeah, there's some of the code there. I've got, what server am I on here? I've got a GPU example here that's kind of cool too. So this is on that same machine, the 4 GPU. This guy here. Yeah, so essentially you can run it either on the CPU explicitly. If you don't specify, or like TensorFlow actually kind of does heuristics beneath the covers and tries to figure out when it's best to move to the GPU, if it's best to stay on the CPU depending on the workload. But here we're actually pinning it straight to a CPU. Here we're pinning it to a single GPU, but because we have 4, yeah, like we might as well. So if we're going to do a 10,000 by 10,000 matrix multiply, we can break it up, spread it across 4 GPUs, and pull it back to the CPU, and then merge the results, right? So I think it goes from like 17 seconds down to 7 seconds. Yeah, that's a single GPU is 15. Yeah, this guy's almost 20 seconds. Yeah, so these are really slow GPUs too. I like the Amazon ones are pretty, they're about 7 years old, I think now. All right, so I think that pretty much ends the TensorFlow, TensorFrames things. Right, like, do you guys have specific questions about those?
So I wanted to ask, to how many GPU instances this thing scales in case of TensorFrames?
Yeah.
When does it pay off to actually use Spark with TensorFlow?
Yeah. See, yeah, so TensorFrames was actually built before TensorFlow Distributed came out. Yeah, I was talking to someone about this at the break, where right now, I think it still makes sense to do everything inside TensorFlow and not necessarily do it this way. It's the fact that, yeah, so TensorFlow first came out, I think, last November, and then the distributed version didn't come out until like February or March. And yeah, that's when like this was being designed. So basically, they were trying to solve the problem where where they wanted to distribute TensorFlow calculations, and specifically, it was around like hyperparameter tuning and grid search, right? Like the classic grid search thing, where it's like very parallelizable. You can try different combinations of these different hyperparameters and spread them across the cluster, and then get back the results, and then figure out which like combination of like hyperparameters is the winner. So these days, yes, I don't really see, there's not that many people using TensorFrames, right? This is all like pretty experimental stuff, but, and I've seen some people use distributed TensorFlow, but you don't really hear too much about it, right? People are like pretty much they're scaling up like to more GPUs, right? Like the new Amazon P, I think has, the P series has like 16 GPUs, I think, on a single machine. So we're kind of at that phase where it makes sense still to go vertical, just because of the like interconnects.
And I guess there is a big difference whether your model fits completely
Yeah.
into one GPU, so
Yeah.
data parallelism versus
Right.
parallelism.
Yeah, I tend to hit this, so actually TensorFlow itself, when you build a graph, it can only be 2 gigs maximum. And those 2 gigs get really eaten up pretty quickly, like when you're training and right, like especially with like recurrent neural nets where you're storing like a bit of state, yeah, right, like you can hit right, like 2 gigs pretty quickly there. That's just the graph definition itself. What you want to do then is, keep data out of the graph and just keep the graph definition is just the edges and the nodes, but actually keep the values stored outside.
So TensorFrames is mostly for data parallelism, right? I always mix them
Yeah.
up.
Oh yeah. Yeah. Data parallel. The same model. Yeah. Across different. I know.
Can you repeat the question, please?
Yeah. Right. Like, how do you? So I guess, how do you know? When what you're doing wrong, right? So, right. Like, how do you keep it from getting that big? Is that kind of? Yeah. Yeah. Yeah, and it's more right, because you can get, right, like the inception model, for example. Yeah, like my point there was that it's the data that you have the option to store in the graph or outside the graph that contributes most to it. So if you stick to, yes, I'll show you guys the inception model here. This is a pretty big, like relatively pretty big graph. And man, I cannot get the like Google guys to like tell me, oop, you guys can't see it, to tell me how they got to this. And basically, I don't think they can explain it either. But yeah, this is the inception model. So this is the model that was generated from, I think, 1 million, right, like labeled images that happen to have a lot of cats and dogs in them. Yeah, because everything comes out looking like a cat or a dog. And yeah, so there's some places here where it just drops down to something like that. And I think there's 1,000 labels. Actually, I can show a quick. Do demo pipeline classify. We can take an image here. I was doing a talk at this company Zillow. It's like a real estate company. So here I'm just taking an image. It's an image of a kitchen. So this is where it's doing just the forward pass, right? It's trained the model. It's doing a forward pass. It's taking the top 5 ranked, right? So if we kept going, all these numbers should add up to 100, right, or 1. And yeah, it's most confident that there's a microwave in here, that there's dishwasher, stove, plate rack. Yeah, so this is a way where you can take like a human, concept of this image and start to kind of like label it and like categorize it, and then you can make a pretty big assumption this is a kitchen, right? Yeah, so this is useful if you're like taking in a lot of user-generated content. You can kind of have a first-level validation that it's in the right place. So that's essentially that is taking like that image and then running it through that entire. So yeah, how long did that take? That was like 5, 6, 7, 8 seconds or something. It's definitely not the speediest. They're starting to explore. This is where the TPU stuff comes in. Right, like using GPUs on the inference side, on the prediction side, not just the training. And again, that's where, yes, actually, this is being served up by TensorFlow serving, where if we had a bunch of these coming in, it would do the batching, right, that I was describing before. For the forward prop, for the inference, yeah.
For serving.
Yeah.
So this is Google Lanet, right? Maybe I'm counting it wrong, but I think it has like 10 million parameters. So the size of the model basically boils down to the size of the matrices in your graph, right?
Yeah, yeah. But you're, yeah.
Or maybe I'm reading something wrong. So.
Yeah, so there's another way too. Yeah, there's something else you can do where you can actually train at full precision, right? Train at 32-bit, maybe 64-bit precision, and then you can right? You can quantize it down to something like 16-bit or 8-bit, right? Like half precision or quarter precision, and then that's what you actually store on your phone or on like a small. So I took I think this was 100 meg, and I got it down to 22 megs. Yeah, by going down to the 8-bit like doing 8-bit quantization. Um, and it was still taking the same amount of time for the inference, which was kind of crummy, but it can actually fit on the phone.
So I think the authors of Google Net actually say that they explicitly optimized for minimum number of parameters and operations. So that was their main goal. Instead of throwing like lots of hardware, they actually try to be efficient. And they won some big competition. There is a competition each year. I think it's ImageNet, right? Which is classifying images, saying like there is a monkey or there is a person. And each year different companies win. So I think 2014 it was Microsoft, 2015 it was, Google. 2015 it was Microsoft with 1,000 layers, residual network. Okay, but then they tried also with 1,000 and it worked. So yeah, okay. So yeah, the number of layers is increasing. It's probably more layers than we have. And this year, ImageNet.
Oh yeah.
I think they are actually. Yeah. And there is another interesting competition where I think it's called Pascal, where you have to find objects on the picture and draw a rectangle and say this is a monkey and this is a banana. So not just classifying images.
All right, so I'm going to jump back real quick and show. Here's an example of us building a model. This has less to do now with TensorFlow here, but okay. So here, this is the classic R data set, the census, like training data, like census data set, where we're given a bunch of parameters for each user, their marital status, their race, their sex, all that stuff. We're trying to predict their income, which is fun, right? Yeah, so here's some Spark code, just kind of setting things up here. Here we're actually pulling the data set from S3 directly. Here's the data. Let me actually just run this here. And after here's the actual, so I'm kind of mixing in here some R, just for those of you comfortable with R. If you're comfortable with this goofy syntax. Yeah, and then we're building a decision tree off of this data. We're fitting the pipeline. So the big revelation that happened with Spark ML about 3 or 4 releases ago was this concept of a pipeline, right? Like the ML pipeline, not just like the individual model, right? Because any new data that comes in has to go through the same pipeline, essentially the same transformations and right, like normalizers and standardizers and things like that. So before, I think it was around Spark 1.3 or 1.4, it was just kind of this hodgepodge of. So they finally decided just to follow the scikit-learn concepts of transformers and the estimators and things like that, the evaluators, whatever. Okay, so here's the situation. We built the model. We've got the whole Spark pipeline model. We are going to use some code by this guy Vilu, who I keep calling everyone. I keep thinking like everyone looks like Vilu. He was supposed to come tonight. Do you know which part of Estonia he's from? Vilu?
I think Tartu. At least I
Tartu?
have known him from my Tartu times. So.
Oh, yeah, that's right. Yeah, like you actually know him, right?
Yeah, I've met him 10 years ago.
Everyone knows that, yeah.
Yeah, that's true.
Yeah, Vilu decided not to continue with his PhD or something and decided to work on code. So,
PhD in chemistry.
Oh, yeah?
I think so. Yeah.
So, Yeah, so VLU, this project is actually gaining quite a bit of traction. Yeah, he's got some goofy licensing around it that I'm going to try to talk him out of, but there's big companies using it, right? Like Airbnb like uses this, and it's essentially a way to deploy your models. So here, this is still within a Jupyter notebook. We've got the model there. We're converting it to PMML. Here's PMML in all of its glory. And then here we're actually deploying it to a live running server. So here we got status 200. This is that same server that was being served up by this guy here. There would be a fourth one added here. There should be. Okay, and then here we actually are doing the evaluation side of it. So here we're passing in data, all data except the income, of course, and asking to predict. Right, like we're not doing any right, like holdout data or right, like model validation here. This is all. And then let's see, we have 96% saying this is less than 50K and greater than 50K, about 4%.
I wanted to ask, how do you extend the JPPML? Like, how do you add new kinds of models or modify it, evolve?
Yeah, you have to work with VLU, I guess, to get that. So, I mean, you wouldn't. Well, for the Spark ML stuff, there's a fixed amount of models in Spark, right? So
if I code up my own model, how do I? So
yeah,
I'm a company. I write my own model.
Yeah.
How it makes from data scientists' workflow to production.
Yeah, if PMML supports it, which I mean, I don't see why it shouldn't. Right, like a lot of people.
I suppose I'm a math genius. You know?
Yeah, and there's something in there. But yeah, I mean, PMML has been around for a while. I think it should, probably. But yeah, if you want to participate in this, the thing is if you can get it, and he's got other projects here. He's got like R to PMML, and I think he even has Keras to PMML. So Keras is a layer on top of TensorFlow that you would write to that kind of makes more, like human grokkable sense, and you can plug in Theano, or you can plug in. But what's cool is that there's this Keras to PMML, which I've never used, but kind of paves the way a little bit. Yeah, so once you can get it into PMML from, if it came from R, if it came from TensorFlow, if it came from like anywhere, yeah, you could deploy it in this particular runtime.
All right. So any more questions?
Yeah. Versus TensorFrames? Yeah. If you already have like a legacy Spark cluster, then you can take a look. I mean, I just upgraded to 2.0 and it all broke on me, so it's still pretty experimental. It was tested under 1.6 and Scala 2.10 and not 2.11 Spark 2.0. So yeah, I mean, I don't really know too many production deployments, yes, outside of like Google, of course, of just pure TensorFlow itself. I've got a couple of friends experimenting with it. This one friend runs this company that has gambling, right, like behind just normal games, right, like gaming. Yeah. All right. To train a convolutional neural network? Or okay. Yeah. So
please repeat the question.
Yeah, the question is so for this specific use case where you've converted audio, it's like an audio problem into, but there's still a time series aspect, right? Yeah. Right, but how do you preserve the concept of time with just a convolutional? Yeah. Oh, that's all. Oh, gotcha. So there's one image per Got it. Oh, I see. Yeah, I mean, there really isn't a way to do it with Spark ML, right? I mean, the convolutions aren't, the support's just not there. TensorFrames, I mean, it would depend. You're storing binary data. Yeah, so I mean, Spark isn't really going to get you much there, right? Like, were you doing single node TensorFlow, or did you actually get distributed TensorFlow to work?
To be honest, I don't know because I didn't build the model myself.
Mm-hmm.
But my colleagues did. I could ask later.
Yeah.
Yes.
Yeah. Did it work? All right.
And so the accuracy of recognizing is like 84%.
Yeah, there's this cool project I was just reading about. It's called like Alpha Toe, kind of like AlphaGo. The tic-tac-toe version.
So this TensorFlames. So like, can we use it? Would it be better to use TensorFrames, or
well,
what would it improve? Or
yeah,
anything?
the question is TensorFrames? What would TensorFrames give you? I mean, the only thing it would give you would be distribution. But see, Spark plus like binary data isn't very, it doesn't work very well, right? Like Spark is good for like chunking up things and text and that kind of stuff, right?
How much training data did you have? $5,000. And how many parameters your model had?
Parameters.
I'm not exactly a machine learning guru, maybe there are any here, but like the more parameters you need to train, the more data you need. So if you can do time frequency transform and get a spectrogram and then train something like, I don't know, SVM on that, I don't know what you did exactly, then it might be, for your case, a good solution. If you had like a huge amount of birds information, you might be able to, I don't know, train recurrent neural networks with long-term, short-term memory. And
there was lots of data available. So let's say we have a very large repository. So it's up to us how much data we can use.
Google does speech recognition with recurrent neural networks with long-term, short-term memory cells. LSTM. Or American version GRU, gated recurrent units, which is just simpler. LSTU is Swiss thing. Or you can ask Christian Coriosan. By the way, small advertisement. We have also machine learning meetup, in case you have been living under a rock. And next time it's on 13th of December, and Christian Koros will tell you about self-driving pizza delivery robots and computer vision problems there. Sweet. Wave your hand.
Yeah.
Yeah. Somebody had a question.
Can I ask you a bit general off-topic question as a practitioner?
Mm-hmm.
Because it is not so frequent that I can see such a practitioner as you. You see, well, for example, about 50 years ago, there was a problem, for example, in software development field, because software development was just try and fail. Some guys just entered some code into the machine. Mm-hmm. It was buggy, failing, and it was like a very applied thing. There were no academic basis, and then academic basis started to develop, and now we can develop software of arbitrary complexity. So to say, it can be scaled, it can be predicted. Currently in machine learning, especially in more complex machine learning as in deep learning, we are basically on the same path. We're poking, trying, failing, and everything is very, very applied. You just tried something out.
Yeah, the empirical.
Are there any developments in that field that, is there actually a hope that it will be put on solid theoretical academic foundation? I want to ask this question because I don't know how to Google it.
So is it about machine learning, deep learning, or big data?
Machine learning and deep learning in particular, because it is one of the most cutting edge things in machine learning.
Aren't you going to this?
I'm going. Yeah.
Are you going to NIPS? Yeah. Right on. Yeah. Yes, you tell us when you come back.
Okay.
No, I mean, yeah, this has always plagued neural networks, right? Specifically. I mean, things that are popping into my head that have become, well, but it's still sort of unknown why, but right, like things like 3x3, right, like convolutions, those seem to be kind of the sweet spot, to the point where the NVIDIA guys have even optimized, right, like GPUs and CUDA and CUDNN, which is the, for 3x3.
But it was discovered by poking, trying, and failing.
Exactly. Yeah, that's why I kind of hesitated a sec there, but yeah, no, I mean, like I said, even with that big Inception one, I can't get anyone to tell me how that came about. Yeah, other than just empirical. But yeah, do you have any thoughts?
Hello.
It's too late.
Sorry, I wanted to ask how this CUDA part looks like. Is it some?
Oh yeah, yeah. It's like who's speaking?
Does it generate some raw C code, or
Yeah.
is it using raw C code?
Yeah, it's so at the right, like lowest level, and there's some pretty significant, right, like limitations. Yeah, right, like you write kernels essentially. That's what they're called, and there's qualifiers to say, there's macros and all this kind of, the C stuff, to say this is meant to be a kernel. That's actually what gets executed. But there's like limitations where certain, like it doesn't support the like standard template libraries and things like that, right? There's a,
Sorry, but could you use Trust then?
Yeah, sorry, what was it?
If you need a standard library, then couldn't you use Trust?
Yeah, you're sort of in a sandbox that has been, right, like it's been sort of opened up partially by the NVIDIA folks, right? And that's just, I'm trying to see if I have an example here. Where's that code?
I mean, you can read the source code. It's not much different from SciPy or Scikit.
I'd like to see the source code.
It's different than, it's a lot different than Scikit. It's ugly. It's barbaric. You spend a lot of time trying to use, shared memory space, things like that. There's this concept, it's called occupancy, and it relates directly to how how much time. Yeah, so typically like you want 50%, right, like occupancy. Yeah, that's a good, and that's right, like how much time your kernel spends on the cores, right? Yeah, actually executing versus doing background stuff or right, like halting, waiting for data dependencies. So here's an example. I can't seem to make this bigger. Hang on. I don't know what's up with Sublime. You spend a lot of time, so there's these, right, like conventions for naming the variables, like H would be host. So host is your like CPU essentially. And D is device. So here you're actually allocating host memory on the CPU. You're doing raw, right, like mallocs here. This is just generating test data. Now we're actually doing the CUDA malloc, which is on the device. Here we're doing the physical mem copy between, you give it the device, you give it the host address, and then you tell it which way to go, host to device or device to host, whatever. So host to device is on the way in, and then This right here, this is your kernel, sum arrays. Yeah, here's an example of the kernel right here. But you're very aware of like which thread that you're operating on. Threads are grouped into blocks, and you have to be very, very careful that what you're doing inside of here is like very data parallel. So otherwise you, so yeah, this is where you actually define it. There's this qualifier here. It says it's global, and this is where it's actually executing. These kernels always take in the grid size and block size, and yeah, these are like CUDA terms. Here.
Yes. Well, I invite you to read the C code of linear algebra libraries for regular CPUs, not that much different. Or Intel has this math kernel library, which is like multi-threaded, super optimized sim vectorized.
Oh, is that the ATX? Oh, MKL, yeah.
But let's continue any discussions with alcohol, and let's thank our speaker. And
Yeah. Woo.